So I'll talk about geometric statistics that we also heard something about yesterday. Yesterday was mainly from a computational viewpoint. Now I will discuss it more like the construction and like theoretical aspects of it. And then of course I'll do visualizations like this one, and that you already saw yesterday. So now you know how I did the visualization. Okay, so geometric statistics is the statistical analysis of geometric data, for example, data on manifolds. And as I said, Nina gave an introduction to that yesterday, and I'll sort of continue on that, but I'll take a slightly different viewpoint on it. So I'll define the statistics. So you can say like most sort of classical geometric statistics is defined in a least square sense. For example, you have 2 points, you measure the deviation between the 2 points by the distance between them, which is the same as finding a shortest curve between them and then taking the length of that curve. So that's how much they deviate. And that leads to the squares construction, for example, the Fraser mean that we also saw yesterday. But what I will sort of try to convey here is a different take on geometric statistics, where we, instead of having sort of this metric or these squares sense, then we will look at probability distributions and then maximizing parameters of those, so taking a more probabilistic view towards the geometric statistics. And so that will be the main theme of the talk, but I'll start sort of with some like examples to motivate why this makes sense at all from a modeling point of view. And then later on in the talk, I will get more into properties of the constructions that you get out of this, and one particular example of that is what's called the diffusion mean. So yesterday you saw the Fraser mean, and now I'll talk about the diffusion mean and how that behaves statistically. Okay, but as I said, I want to sort of start by motivating that, and that motivation comes, for me at least, from shape analysis. So the shape analysis being one case of geometric statistics, like each shape being one observation in a high-dimensional shape space. And then if you do the same trick as you do here, measuring distances with shortest curves, then you get something like the difference between these two shapes by a smooth trajectory between them. But now taking the probabilistic view, we go from like a smooth trajectory to something which is stochastic. So that's sort of where I want to start. And what you'll see is a collection of material from different papers and with different collaborators. Okay, so let me start with the shape analysis point of view. So as I said, we have shape data, and that means each observation is one shape. They can, for example, be represented in a discrete way by landmarks, and then you get a data set like this, which is a number of observations of the human corpus callosum taken from MR images, but then represented as by the outline with these curves here. And then in shape statistics, we would like to do statistical analysis of these observations. So for example, finding the mean, some kind of representative shape of the data set, or do things like principal component analysis, but what is the variation in the data set around the mean, for example. So this is what you see in example up here. Or maybe fit a probability distribution, look at what is the variance sort of point-wise along the shape. And the reason why this is interesting from a theoretical point of view is that shape spaces are non-linear, so we cannot use like regular multivariate statistical tools to do this analysis. Instead, like usually shapes are represented in non-linear, but like smooth non-linear spaces, so manifolds, so we turn to geometric statistics, and then we can use the statistical tools coming out of that. So these shapes should be seen as one example of geometric statistics objects. Okay, so let's look at how shape analysis can be pursued in a concrete way. So there's many different ways of representing shapes and working with shapes, and here you will see one of them. I think actually Martin will talk about a different viewpoint later on. Okay, so this way of looking at shape is that we model the differences between the shape by deforming the domain wherein the shape resides. So here's one shape, you see like a grid in the background, and then we make a deformation of the domain. You can see that by the grid being deformed. We let the shape follow, and that gives us a new shape. So that this deformation is mathematically a diffeomorphism between from the domain to itself. Okay, so that's a nice way because it's very general. We can have a point representation of the shape. We can also take a full outline, and we just do exactly the same. We let the shape follow the deformation. And okay, so more precisely, we would say that if we have phi is a member of the diffeomorphism group, we have an action of the diffeomorphism group on the shape. And in this case of landmarks and curves, the action is by composition. But you can also have you can also do the same with images, and you have a different action, but the idea is the same, that you sort of deform the domain. Okay, so when this is done in practice, then so first of all, we need to find out if we're not given this deformation, we need to find it. So we need to somehow say, if we do this deformation, when is this shape close to another shape? And that is modeled by a similarity measure that says, like, what is the difference between phi acting on the first shape in comparison with the second shape? And if you get a perfect match, then this term here will be 0. And then there's a regularization, and the point of that is to choose between the infinitely many diffeomorphisms that can do the matching here. So we want something that is regular, and that's encapsulated in this regularization. And then having these two terms, we get an entity, and then we can minimize that entity, and then we get a suitable deformation out. So this is also, this way of looking at it is often called the LDDMM framework, or large deformation diffeomorphic metric mapping framework. Yeah, so so we're working with diffeomorphisms. They deform the domain. We can look at the whole diffeomorphism group, or maybe a regular subgroup of diffeomorphism group, and we have at least in there the identity mapping that does nothing, and then we can do this deformation of the shapes from one to match the other look at it as a gradual process. So we sort of move in the diffeomorphism space, deform the shape gradually. Here's another example, like you have this corpus callosum shape, then you gradually deform it in order to get a different shape. And your final phi that I have on the previous slide would be the endpoint of this path of diffeomorphisms. And this way of looking at it is nice because that allows you to build this regularization term as an energy of the path in the diffeomorphism group. So here we integrate up from time 0 to t, the derivative sort of as a tangent vector in the diffeomorphism group, and norm of that, and that in turn gives us how irregular the diffeomorphism is. So when we match up two shapes, we minimize this energy here in order to get a regular diffeomorphism. Okay, so yeah, as I said, this is also called LDDMM, and one consequence of this is that you can look at these optimal paths as geodesics for a Riemannian metric on the diffeomorphism group, a right invariant Riemannian metric. So in particular, they will be very smooth. So with what we had before, we can do actually these squares constructions. For example, we can measure differences between two shapes. We could also find a mean shape by finding a Fresian mean-like construction. But what often then occurs in reality is that the transformation between two shapes is not as smooth, like a very smooth process as what we just saw. Often there's noise in the picture as well, and often what you will observe is something that doesn't take a smooth transformation, but some kind of irregular transformation from one shape to the other. Or if you plot it on the shape level, you will see something where sort of each point on the shape irregularly moves in order to produce the new shape. So this can, for example, happen in evolutionary biology. You have time goes by, there's genetic variations in your species, and then if you look at the shape of the animal, then it will stochastically vary as time goes by. So then somehow we need to put that into the model, and one can think of taking the smooth geodesic equations that we got out of the previous model and then add noise to it. And that gives you a stochastic differential equation. There's often a deterministic term here, as there was in the geodesic case, but then you add also noise and you get a stochastic process. And now we are sort of this was the motivation of starting this looking at probabilities and stochastic processes and so on in geometric statistics, because like this is an example of a model where there's actually a stochastic transformation of the data happening, and we would like to model that. Yeah, so I said evolutionary biology, and here is like an example of a shape transformation of a bear skull to another bear skull. And if you look closely, maybe it's not really visible on Zoom, but this shape transformation in here is stochastically varying in time. Yeah. 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 Yes. So that's a very good question. So I don't have a slide that actually really used, but I can sort of sketch it. So you have evolution. You have your species. Maybe you model the shape of the area species, and it will vary as time goes by. And then at some point it will branch out into two subspecies. It keeps on stochastically varying, but now it will be independent between the subspecies. And that branching can happen again, and you get like a tree structure. And then what you observe when you, like your biologist colleagues, go out in nature and like pick up the shapes, they observe what is the values at the leaves of the tree. And the variation in those leaves will be dependent on the branching structure of the tree. And what you are essentially interested in is to re-infer the tree from the variation in the leaves. Yeah, so this is like, yeah, so now we haven't really specified the stochastic process yet and so on, but let's say we do that, then we have a model where the tree is unknown, but you can think of that as a parameter of the model, and then you have your observations, and then you can infer the tree from that.
So the aim is to reconstruct the whole tree, or just to do some representation learning and say how different some species are and how far in the past?
So depends on how ambitious you are. Like in principle, reconstruct the whole tree, or as much information you can get out of the shapes. In genetics, entire trees are inferred from gene observations. I think it's too ambitious to say that from shape observation you can infer an entire tree, but you can either like make a better inference of the tree if you couple it with genetic data, or you could say that like we think we know the tree from the gene data. Now we like to, for example, infer the branch lengths, or say like what do you think the animal looked like 100 million years ago, or stuff like that. So, yeah. This skull. So this is a 3D CT scan of a wolf skull, and like when it stops, and then it's just like a cut through it. It's a 3D CT scan. Yeah. And actually, like this is a PCA plot of shapes of skulls, and an example of this phylogenetic tree that I just talked about is like plotted on top here. So, but it's not really so visible. But there is actually a tree structure sort of in there. So what I have showed now was landmark-based, but it's not specifically tied to landmark representations. You can also take the full outline, for example. You can have a similarity measure that is invariant to reparameterization of the shape. Yeah. But I think like you should more view what I say here as like a general way of looking at shape data, and then how you explicitly do it is depending on which data that you observe and so on. For example, for the 3D data here, I would not use a landmark model. Okay, but let's like sum up these two views on doing statistics for manifold value data, and not like for now just look at the shapes as one example of manifold value data. So what we saw yesterday was, for example, the Fresnel mean of data. Now the data would be the red points here on a sphere. The Fresnel mean is somewhere in this case around the North Pole, and it was computed by minimizing geodesic distances. So somehow there's a model of geodesic evolution from the mean to the data points. And when you find this geodesic, you can match them up exactly, and that corresponding to minimizing this energy function that I had before in the shape case. One can either do that so that you exactly hit the shapes, or exactly hit the points here, or you could also account for a bit of noise, and you get an inexact matching. So this is actually a little bit inexact. And okay, so you get distances out of this energy because there's a Riemannian formulation and so on, and then you can do Riemannian least squares, for example, to find the Fresnel mean. Yeah, it's good. It would actually be the R. Yeah. Because like, yeah, but I would, if you do, let's say we do exact matching, so that now the shapes after deformation match exactly, then this one would be 0. And then the amount of sort of effort you need to deform one domain in, like, that is captured in the R term. Yeah? I think my answer would be that I will switch to this more probabilistic view, and then the S term would be sort of additional noise in your observations, and then it will come like out of that. Yeah, so like clever way of avoiding to answer the question, I think. But it's a good question. Okay, so that was the squares view on how to do this. So let's take this more stochastic view. So now in the shape case, we had these stochastic processes. If we look at like the S2 case here, now from the mean to each data point, we have a stochastic process instead of a smooth geodesic. Now if we start here and condition on hitting here, or we start one shape and condition on hitting the other shape, we get a stochastic bridge. It's written like this. And so it's time dependent, and at the end time capital T, you can just think of this capital T as being 1. We condition the one shape to hit the other. And then you can have noise in your observations as well. We add a little epsilon here, and that corresponds to exactly what Martin's question before with the non-zero similarity term. So this is like inexact matching, but in the stochastic way. Okay, so now the square distances that we had before becomes the equivalent of that in this setting would be the negative log transition density of the stochastic process. And if you want like a Euclidean version of this, then if your stochastic model generates a normal distribution, then the negative log of the normal distribution would just be the square norm, so that corresponds to square distances. So in the Euclidean world with normal distributions, then what I had here was exactly the same as what I had in the deterministic case, but in the nonlinear setting, it becomes different. And then I can think of doing my statistics, like finding means and so on, by maximizing minimizing the negative log likelihood, or maximizing the likelihood, or sampling the posterior distribution, for example. So this is where I like to go. Okay. And then this slide is just to say that now I've shown you shapes and so on, but geometric statistics is of course much more than that. It's like data on S2, modeling data on the world, graphic data, or it could be 3D directions, it could be angle on tori for protein structures and so on. So it's more general than just shapes. Okay, so now you know sort of where I'm going, and then I will talk about a bit about how to actually get there. So think about the stochastic process. It starts at a point. It's on a manifold. Now we have data observations, and then we like to ensure that the stochastic process actually hits our observations. And you say if we manage to do that, then out of that, eventually we will be able to get the likelihood. Then, so that we can optimize that to, for example, infer the mean value. So the question is now, like, how can you actually do that? And that is called bridge sampling. So sampling stochastic processes conditioned on points, and that's like maybe an easy thing to formulate, like you just wanted to hit somewhere. But it's actually doing it in practice is really difficult, even in Euclidean space. And there's a whole community in statistics that looks at efficient simulation of condition diffusion processes, for example. We are in the manifold setting, nonlinear setting, so it's even more difficult here. But let me just sketch like how you can actually pursue this. So here is like, just keep it simple. So this is Euclidean space. So we have a stochastic differential equation. It has a drift term. It has a stochastic term here. And it starts at a point. Let's say it starts at 0. And now we would like to force it to hit this target point V. So if we don't do anything, then it will like radiate out in all kinds of direction, and the probability of actually going there will be 0. So how can we ensure that it goes there? Well, one idea is, like it was put out by Dina and Hu in 2006, is to make what's called a guided proposal process. So that's the original SDE, but now we add a term here, a forcing term, a new drift term, that takes the difference between the current value of the process and the target, and then forces it that way. And it does so with increasing force, because like capital T was our end time. So this denominator here would go to 0, and then the forcing term would go to infinity. So if it doesn't hit, then this will for sure blow up. But then what Dina and Hu showed was that in a nice like setting, you need this sigma to be invertible, for example, and so on. Then it will actually in the setting hit V almost surely. So that's good. They also show that the process that you get out here is absolutely continuous with respect to the true conditional process. It will not be equal. It will have a difference in measure, but it's absolutely continuous. So it's like a good approximation, hopefully. And they also gave an explicit way of computing the difference in distribution between what you actually wanted, which was the conditional process, and the result of doing this guiding construction. And that difference is a likelihood ratio. It's like also called phi, but it's something that you can compute explicitly. So in reality, you can take this guided proposal, you can sample a lot of times from it, compute your correction factor, and that gives you an approximation of expectation over the conditional process. Then that will in turn allow you to get the approximation of the likelihood. So that's like the simplest Euclidean way of approaching this bridge sampling problem. Okay, so but we are in a geometric world, so the one thing I've looked at is to support this to manifolds. So for example, well, now we start at the North Pole. We want to condition on hitting there. That maybe goes fairly well, but if we are in a cylinder, we start on one side, we want to condition on hitting the other side, then maybe you can imagine that it's more difficult than the Euclidean case, because then you can go either side around the cylinder. And what turns out to be mostly sort of problematic in this case is accounting for the cut locus of the points here. So what will sort of show up in your guiding stochastic differential equation is that this guiding term, which is now not a vector difference, but the log between 2 points, the Riemannian logarithm map, is that when you cross the cut locus, then you would have like a rapid change of direction, a discontinuity in the gradient field. Okay, but this can be accounted for, and then you get sort of ways of doing that, and in turn, then you can, for example, approximate the heat kernel on manifolds like this by repeatedly sampling these guided processes. Okay, here's just like the theorem. You can do the same. You can take expectation over the condition process by using this guiding scheme, and you get this likelihood ratio that I talked before. And what you, if you look into sort of the expression, then you will see that's a local time when you have this cut locus crossing, and that's sort of the main difficulty of accounting for that. Okay, so that was like general Riemannian manifolds. You can also look at this in a Lie group setting. Then it becomes a little bit more approachable, because well, if you have a Lie group, then it's parallelizable, so we can do everything in the Lie algebra, and then you sort of, yeah, you have this vector difference and the guiding terms and so on, but you formulate it in the Lie algebra, and it becomes a little bit nicer. And I looked at that like both in Lie groups, but also in homogeneous spaces. So here we look at S2 being the quotient of SO3 modulo SO2, and here you see an example of a bridge on S2 lifted to rotations in R3. Okay, so that was like a key ingredient of actually making it work and actually sampling these conditioned process, and then we get the likelihood out of that, so we can optimize it afterwards. But then let's look at it a bit more at what it actually sort of what it means. Okay, so back to this idea of these squares construction on one side and probabilistic constructions on the other side. So the sort of classical, we have data on a manifold. We want to do statistics. What is the first thing to do? Well, it's computing the mean, and like the way that this is most often done and traditionally done is to compute the Fraser mean. And the Fraser mean, as we said a couple of times now, is the point on the manifold that minimizes the square distance to the observed data. So this is kind of established. This is how you get a mean on the manifold. And if the manifold happens to be Euclidean, this would correspond to the expected value. So that's sort of all good. But you can also define the expected, like the mean in the Euclidean spaces in different ways, and then you can think of like if you generalize those instead of these square constructions, what do you get then? Do you get the same, or do you get something different? And of course, as you can imagine, in a nonlinear setting, you get different constructions depending on what you generalize there. So one thing that you could think of generalizing would be to generalize a normal distribution and then look at the mean, not as the center point of the distances, but as the mean of a normal distribution that maximizes the likelihood of the data. So, sort of following the program that I sketched so far, we define a family of probability distributions on our space. We have our observed data, then we compute the likelihood, so that's the density function evaluated at all the points, multiplied up, and then we maximize parameters for this likelihood. And one specific example of doing that would be to start a Brownian motion on the manifold, let the parameter theta be the starting point, and then maximize the likelihood of the starting point given the data. And then we call the starting point the mean, right? And again, just as for the Fraser mean, if you do this in Euclidean space, the Brownian motion just generates a normal distribution. So then the starting point would be exactly the expected value. So the same as the Fraser mean. But as soon as you move to manifolds, then you get a different construction. And this we call the diffusion mean. So what I will talk a bit now about this diffusion mean is how does it actually sort of deviate from the Fraser mean. Okay, yeah, just one more example to sort of get the point. Like starting point on the manifold, run the Brownian motion, and then you have your data points, and then you maximize the likelihood, so that's finding the most probable starting point of the Brownian motion. And then you get like a stochastic picture like this, and just to like sort of contrast it with the Fraser mean picture, the Fraser mean picture would be like this with the smooth transition from the mean to the data point. So somehow maybe you can also see that this kind of senses the geometry more than what you have in the Fraser mean case, because these stochastic trajectories will sort of like they will sense the entire manifold, right? So they will move around everywhere. Actually, I just want to go a little bit forward and take this first. Okay, so let's look at these differences between the means, one being the Fraser mean and one being the diffusion mean. So to start with, then let's look at uniqueness and then take a very classical example from geometric statistics of sort of non-expected behavior of the Fraser mean. So this example is that you have a probability distribution on the sphere that is singular at 2 points, mass at the North Pole and mass at the South Pole. And we divide the mass between the two, and we usually think of having most mass at the North Pole, so you would expect the Fraser mean or the mean value to be up here. But what happens then is that the mass at the south pole actually disturbs the picture a bit. And if there's enough mass at the south pole, then the Fraser mean will not be the north pole. It will actually not even be unique. It will be like circles around the north pole, depending on how much mass you put at the opposite point, the south pole. So one question here would be, okay, that's for the Fraser mean. What happens with the diffusion mean? Somehow the diffusion mean, so we run a bounding motion for some time or model a normal distribution. So somehow we are sort of in the model putting mass everywhere on the sphere. So maybe it will behave differently, and that's actually what you see. So you have this extra parameter for the diffusion mean, which is how long do you run the diffusion, and that's corresponding to the variance of your normal distribution. And what you see is that if you run it for longer time, or you sort of put more variance into your model, then you can put more weight on the south pole and still having a unique diffusion mean being the north pole. So somehow this non-uniqueness that is a feature of or property of the Fraser mean is less appearing in the diffusion mean. The M here is different, like this is S2 and this is S3 and so on. I mean, in Euclidean space, a mean would be somewhere in between. Yeah, but this is like I don't think we can really make a Euclidean comparison. This is like, it happens because it's put on the chord locus there. But when you look at it first, then you were saying there's most mass at like, if you want your mean to be a good descriptor of your data, and there's most mass at the north pole, then you would expect your mean to be at the north pole. But that's not what happens. And you can see, like, then with the diffusion mean, it does not, like, you can have the same situation where you have non-uniqueness, but it's depending on the time parameter, and the longer you run your time, the higher value the more mass you can have here. And it's sort of like the intuition should be that running your diffusion puts mass in the model, you put mass in the south pole, and therefore it's like the model is better fit to your data than the Fraser mean. And that's an important point actually as well. If you let the diffusion time go to 0, then the negative log likelihood will approach the square distance. So somehow the Fraser mean is the 0 time limit of the diffusion mean. Okay, so that's uniqueness. And another thing you would look at is asymptotics. So asymptotics meaning when your sample size goes to infinity, then how do these mean how do estimators of the mean from your data, how fast do they converge to the true distribution mean? Okay, so in Euclidean space, we have the central limit theorem, and there you have square root n convergence to a normal distribution. So as your sample size goes to infinity, you get something that is, your mean will converge to the true mean, and the variation of the estimator around the true mean would concentrate, and the rate there would be square root n. Yeah, and yeah. Like not an explicit curvature bounds and so on. But you can always in the low time regime, then you are close to the Fraser mean for time, and you have also you have expansions of the heat kernel that are time dependent and so on. Then you can say something. But usually, mostly what you're interested in is when data is really spread around, like when there's high variation, as what you see here, and then it's not a short time case, and then it's very hard to say something analytically. Okay, so this plot here shows you increasing sample size, and here we have variance of our estimator rescaled by n. And so in Euclidean space, you would expect to see the central limit theorem would say that these lines here should be horizontal. So that would be the usual rate of convergence of your estimator to the true mean. Then what happens on manifolds for the Fraser mean is that this rate of convergence is often slower, and that's called smeariness. So like because of the geometry of the curvature, then you get slower convergence of your estimator to the true mean. And usually they are too smeary, and in too smeary case, you will see the line being this dotted line here. So that is like a sig lower convergence rate to the true mean. And here, these curves here show the actual variation plotted as a function of t. And one would be for t0, and that's exactly the Fraser mean case. And here you see that for these data, we are really in a too smeary situation because like this line here aligns with the dotted line, and that's a lower rate of convergence. And then you can imagine increasing your t, and then you see that the lines become more and more horizontal. There's still like a factor difference here, but for high t you get something horizontal. So you can sort of from this hypothesize that maybe the diffusion mean has less of these smeary problems than the Fraser mean. And it actually has sort of real implications, because if you want to get a mean estimate out, you need like a substantially much more data for, in the smeary case to get a good estimate of your mean than in the non-smeary case. Yeah. So is that the case? Can we somehow say that the diffusion mean is or is not smeary? And well, we can say something, but the picture is a little bit blurred. So what we can say is that if we optimize for the position and for the time parameter, for the variance at the same time, yeah, then we get something that looks to be sort of non-smeary, and that's encapsulated in this equation here. So here you have the negative log likelihood, and here is integration over the distribution or expected value, and here is the Laplacian. So that's like the trace of the Hessian, and here is a term that has like gradients of the likelihood squared. And in sort of all non-degenerate situations, this one will be positive. And the only situation where you can imagine that it's not positive is if you have your data like placed exactly at the colocus. So exactly like the two-pole distribution that we had before. But if you have like any like non-contrived situation, like a smooth density or something like that, then you have a positive value over here. So this means that the Hessian trace of the log likelihood will be negative. So said in another way, the sum of second order derivatives of the function that we maximize is strictly negative. And that is exactly ruling out smeariness, except that, yeah, okay, so you can say, like, if your objective function has all the second order derivatives being strictly non-negative, then you are not in a smeary situation. And what we get out of this diffusion mean picture is that the sum of the second order derivatives is strictly non-zero. So some of them could be zero, but if you add them all of them up, you get something that is strictly non-zero. So the diffusion mean here can be directionally smeary, meaning you can have lower rate of convergence in some directions, but not all. So the situation is definitely improved compared to the Fraser mean, but it's not like the perfect picture. And let me just show you why this happens. So we take the negative log likelihood in here, and then we take t derivative of it, so time derivative, and you move the time derivative in, then you observe that, okay, it satisfies the heat equation. It's like a Brownian motion. So this time derivative becomes the Laplacian, and then you take the log again, and then you get the sum of these two terms here, and then we say that we optimize for the position and the time parameter at the same time. So this derivative here with respect to time should be zero. So that's a zero here, and then we get equivalent like these two terms being the sum of these two being zero, and that was exactly this equation that's on the other side. Okay, so like asymptotic, we're in a better situation, but not like it could be stronger. So like if this could be improved, I would be really happy. Yeah, actually here you see the same situation happening, but with finite samples. So it's not only an asymptotic property; it also happens with finite samples. So I think in the last 2 minutes, I'll try to sketch like how I think that we maybe could improve the situation, but also where I haven't really reached the goal yet. So this is more like a speculative or like how to go there kind of idea. So we have data on our sphere. In the diffusion mean, we fit a Brownian motion to the data. So the statistical model is something that looks like a normal distribution, and it has the same variance in all directions. But often the data would look something like this, where there's more variation in some directions than others. So somehow, if we fit like a diffusion mean to this picture, we are kind of in a misspecified situation. We are fitting a statistical model that has the same variation in all directions, but our data has more variation in some than other directions. You had a question? Yeah. Yeah. Yes. So what I mean by normal distribution is like if there's no covariance, then I just mean run a Brownian motion until some time and stop it, and that's what I think of as normal. But now I want to model like this kind of thing, and you're exactly right that that is not something you just do. So how can you do it? So you could, So what you can do is that you can look at the frame bundle of the manifold, and you can phrase the Brownian motion as a diffusion process in the frame bundle. That's the Ellsworth-Immediate construction of Brownian motion. Usually it started at a point and a frame that is orthonormal, then you get the Brownian motion. But you can also start at a non-orthonormal frame, and then you get a kind of this variation, more directions than the other. I think maybe if you want the full story, then I can, we can do it offline. In 1 minute it's a bit too much. But sort of the upshot of doing frame bundles and so on is that you get distributions on the manifold that has kind of non-trivial covariance there, but it's still tied to a diffusion model, but now just a diffusion model in the frame bundle. So here, there is what I would like to end up if it was possible. So like now I'm fitting distributions that still arise from a heat flow, but from this frame bundle picture, and they do get like non-trivial covariance, so somehow they are much better fitted to a situation like this than what I had if I just took the diffusion mean that was based on the Brownian motion. And like in the diffusion mean setting, we optimize just for the time and the starting point, but now if I do this trick and so on, then I also need to optimize for the covariance. So what I optimize here is the starting point, but also a symmetric positive 2 tensor corresponding to the covariance. And it's in the bundle of symmetric positive 2 tensors on the manifold. So that is called like the anisotropic diffusion mean, because it also fits the diffusion direction-wise. And then one could hypothesize that this situation that I had with if you optimize for both time and position, then you would get non-smeariness. You get the second order derivative with respect to the position to be non-zero. And well, why could you actually think that that could be true, except because it makes sense? Well, you can take derivatives of the heat equation with respect to vertical variations, so that would be like variations of your frame or the covariance in different directions. And if you do that, well, then you need to take care of commutation of the Laplacian and vertical derivatives, and out you get a term here, which is the direction derivatives second order of your density, and these are exactly the ones that you would like to be non-zero. And ideally, this will all work out to be that they are actually non-zero in the optimal situation. But as you can almost imagine from how I said it, it's not quite the case, and there's like those are some additional things that you need to assume, that the situation is not too far from like the likelihood surface is kind of matching the variance and so on. But also one thing is like diagonalizing the Hessian with respect to spatial derivatives, but there's also diagonalizing the Hessian with respect to now variance derivatives, and these two can rotate in different ways, and then things don't work out exactly. So work in progress, maybe we can show more, maybe we can say that it's non-smeary in this situation, but it's not all the way there yet. And I think that sort of concludes my talk. Has some references and rotating both scholars. Thanks.